Now we're ready to begin Unit 5, entitled Exponential and Logarithmic Functions. And you might ask why we're dealing with these functions separately from the ones we did in Unit 4, the polynomial and rational functions. Well, the reason is that these fall under a category or a class called transcendental functions. That is to say, they transcend or go beyond polynomial functions and rational functions. So we're going to deal with them separately as a result. And we'll deal with these two types. And I guess it's time to get started. Well, the first type of functions we're going to look at are the exponential functions. But before we do that, we need to define one-to-one functions, because that will become important when we talk about exponential functions and then logarithmic functions. So let's go ahead and look at this definition. First of all, I'm going to be talking about a function, so let me just call it y equals f of x to be generic. And we'll examine what this phrase one-to-one could mean. There are two variations on this, and we'll see what they mean and why one-to-one is so special. Let's first of all look at this situation. 1x, 2, keep the same pattern here, more than 1, f of x. Because that's where the 1 is going from and the 2 is going to. It's going from the domain element of a function to the range element of a function. So imagine that we have one x value that is going to more than one f of x value. Now what could that possibly be? Well, if you remember the little boxes I drew for function machines earlier in this course, you remember that x would go into the function machine, and if the function was called f, say, then out would come f of x. Now here I'm posing the situation, suppose more than one f of x comes out. The same x goes in, but two different or more, non-equal perhaps, f of x's come out. What could that mean, or what's the problem? Well, you should see immediately that the problem is that this is not a function. Okay, functions by definition took in a domain element and put out one and only one range element. And you can see this also by looking at it in a graphical picture. If this is the x value down here, then what we're saying is we get out of it a particular f of x and maybe another f of x. And you can see on the y-axis, you can see visually why this can't happen. If I draw a dotted line down here to f, I'm talking about this point here above x and this point being on the curve, which means the curve's got to be something like this. But of course, as you know, that cannot be the graph of a function because there are two y values for one x value. In fact, another way to say this is that the vertical line test for a function, the vertical line test fails. Okay, that was the test we used for a function. So, when we want to look at various sorts of functions, the 1x to more than one f of x will not be considered because that's not even a function. Okay, let's look at another variation on that. Let's look at the sort of the reverse case. The more than 1x to 1 f of x. Now there's no problem with this being a function. Several x's producing a single f of x value is not a problem, and I'll just sort of draw you the little picture we've had before. There's my little function machine, function f, and maybe we have an x1 that's not equal to an x2, and they both go into the function, and they produce the same f of x. So f of x1 is the same thing as f of x2. They go to the same place. Now this is a function. In fact, let me draw a little graph over here to show you the kind of picture you might get. Suppose you have an x1 that's not equal to an x2 on the x-axis. It is possible, isn't it, that they go to the same f of x height. This is the f of x1 equals f of x2 height. And that would be 2 points like that, and the curve might look something like that. Now, there's no problem with a curve that looks like that. That's a perfectly legitimate function. What I want to observe from this, though, although more than one x to one f of x is indeed a good function, I want to observe, however, that this is not what we might call a reversible function. We'll have to define what that means. But you can see from the picture why that would be so. Imagine that the y-axis is now the domain element, and I want to take this common element fx1, fx2, and I want to go and send it by a function back to where it came from. Well, you see the problem. This would go to here, or it would go to here. Which one? That's exactly the problem we had before when we had one number going to two different numbers. That is not a function. So although this is a function in the forward direction, more than one x to one f of x, going backwards it's not reversible. And of course, just to make sure you realize that you know functions like this, consider the function f of x equals x squared here. And remember that f of 2 is equal to 4, but that's also equal to f of minus 2. So there's a case where two different numbers, 2 and minus 2, go to 4. Okay, well, I've looked at the two cases where I had more than one x going to one f of x, and previously one x going to more than one f of x. Now there's only one case left over. Finally, this is the case we want to look at in this segment. This is the 1x to 1f of x. And that, of course, is where the name comes from, 1 to 1. Nice, simple, explanatory name. The idea about this is that it is reversible. Now, I have to explain that. We'll get a better definition of that. But you can see from the picture that if x1 here is not equal to x2 on the x-axis, and they go to two different places, so maybe this goes to f of x1, and this one maybe goes to some other number, f of x2 on the y-axis, you can see that, dot some dots in here so you can follow this. You might have a curve that looks like that, and this is a curve where different numbers go to different places. F of x1 and f of x2 are clearly not the same. So with that in mind, we can go ahead and define what it means to be a one-to-one function. Definition: a function f is, we'll call it one-to-one. We usually write the words out like that, one-to-one. If for any, say, x1 not equal to x2, both of them in the domain of f, there's my shorthand for that, the x1 not equal to x2, but they're both in the domain of f, if whenever we have two different numbers like that, then under the function, f of x1 is not equal to f of x2. They go to two different numbers. So that's what one-to-one means. Two different numbers always go to two different places. They never go to the same place as, for example, in the function f of x equals x squared. Here's a familiar function we all know. F of x equals the absolute value of x. And here is the picture. The picture really does help you see what's happening here. Remember, it's that 45-degree V, my x and y axes. And you can see from this picture that if I take a number like 1, it's going to go to a particular height here, the absolute value of 1, which is 1. But notice that minus 1 also goes to that height. So this is an example of a function that's not one-to-one for that reason. And if you want to prove it's not one-to-one, all you have to do is show for a particular set of numbers that, for example, minus 1 in absolute value equals 1, and that equals the absolute value of 1. And since these two are not the same, and yet they go to the same f of x, this is not a one-to-one function. Another example to look at, another familiar function, f of x equals x cubed. Well, here's the picture of that, as you know. It's the cubic that comes up there and touches right here at the origin. And you can see from that, without too much difficulty, that this is one-to-one. Because if you look at x1 not equal to x2, then x1 cubed is still not equal to x2 cubed. Okay? Because cubes are going to preserve all the properties of x1 and x2. Unlike the square function, these are actually different. So if you have a number here, it'll go up to a certain height here, and no other number will go to that height. Actually, a visual way to see that, and we'll look at this in a second, is draw a horizontal line through that y value. Notice that it only struts the curve once. Well, keep that in mind, because that's about to have some meaning, and that's the insight behind the following theorem. This is one that really is very helpful in determining, visually at least, what a one-to-one function is. This is called the horizontal line test. Remember, we had the vertical line test, which tested whether we had a function or not. This is the horizontal line test, and this tests whether a function is one-to-one. Or, if you like, if it's reversible. If any horizontal line, any line whatsoever, any horizontal line intersects the graph of a function, say f, in at most one point. Now it could miss it entirely, that's fine. But if it does strike it, it strikes at most one point, never 2 points or more, then the function f is one-to-one. So here's a visual test for you to determine whether a given function that you have the graph of is one-to-one or not. And again, the proof is clear from this, because proof idea here, if you had a function, say something that looked like that, where two different x values, x1 not equal to x2, went to the same y value, then this is not reversible. So this would not be a one-to-one function, and we can see that the horizontal test fails because this horizontal line in particular, it's not the only one, but that's one, strikes this curve in two different places. And since it does strike the curve in two different places, this cannot be a one-to-one function. So that's kind of visually the idea behind one-to-oneness. Well, it would be nice if there were a whole class of functions that we knew immediately were one-to-one. Well, observe, there is a class of functions that's always one-to-one, and they're very familiar functions. And once you see the graph, you realize that that's true. So let me divide this into two here. The first class are the class of increasing functions. If you have an increasing function, and what does that look like? Well, if you remember, an increasing function takes two different x1 and x2 values, and it might look like this. It goes to two different f of x1 and f of x2 values, where the f of x1, see, this is x1 less than x2, f of x1 is less than f of x2. And you can see that means that the further one is higher, and that means increasing, because we measure increasing from left to right, remember. Likewise, decreasing has a property that's similar. If we have our x and y axes, and we have a curve coming down like that, say, and again we take an x1 and an x2 that are not equal, in particular x1 less than x2, then if we come up to the curve, we have f of x1 in this case being larger than f of x2. Now the fact that it's larger, or the situation is reversed here, doesn't really make any difference for what we want to look at. Right now we want to realize that if we have an increasing or a decreasing function, different numbers go to different numbers. Different numbers go to different numbers. So that means we can put this in the form of a really short theorem here. If f is an increasing or decreasing function, increasing or decreasing function, then automatically, because of that little reasoning we did above, f is one-to-one. So for us in practice, it's much easier to test to see if you have an increasing or decreasing function than to generally test if you have a one-to-one function. So we'll see how this all applies in our case of exponential functions, which is what we're about to get into next. All right, now we're finally ready to begin with exponential functions. Exponential functions and their graphs. So let's go ahead and get started. First of all, we've talked about exponentials before in this course. So let me recall some of what you know, and then we'll see if we can extend it to an exponential function. Recall that if we have a to the r power, that is defined for what? Well, let's see. We have it defined for a positive and r being a rational number. Now those are restrictions we didn't really focus on very much before, but now we're going to because there's something missing here. For example, the kind of things that we've looked at are 2 to the 3 power. Okay, that's defined for us. 4.7 to the 1/3 power. That makes sense for us. 893 to the 6.54 power. All of those make sense to us because the decimals, all the decimals that appear here can be turned into rational numbers. And once they're in the form of rational numbers, we can deal with them, as we've seen before. Now we ask the natural question, why did you limit yourself to a greater than 0? And can this be defined for r being an irrational number? Well, let me give you some answers to both of those. Put this in the form of a note here. A greater than 0, okay, let's deal with that first, avoids, now why did we choose a greater than 0 only? Well, the reason is it avoids many undefined, and that would happen as in the case of a equals 0, and you might end up with an expression like 0 to the 0, or 0 to the -1, which would be division by 0, etc. All of those would be undefined, so we want a to be greater than 0 to avoid that, and also, that is one part, and to avoid non-real complex numbers. Non-real complex numbers, such as the situation where we have a less than 0, a negative, then we might end up with something like -1 to the 1/2 power, which of course, as you know, is I. It's a complex number that's not real. So that's the reason we limited ourselves to the a greater than 0 case, so we avoid all these various complications. Now, the next question I asked was, can we define, this is a good question, can we define a to the x, where of course we're taking a to be greater than 0, in the case when x is irrational? Can that be defined? For example, what am I asking about? I'm asking the question, what could something like 2 to the square root of 2 power, or say 5 to the pi power mean? What could those possibly mean? Now we have a sense of what exponents are, but we surely don't understand what these would be at this point. So we want to come up with a definition. Well, the proper definition involves a little bit of calculus, but we can do a partial answer here. And the partial answer is, can we define such things? Yes, we can. And here's the idea I'm going to give you that should explain this reasonably well for a college algebra course. Let us consider, I'll do this by example. Consider any a greater than 0, so that'll be the base of our exponential, and the irrational number, because we want to look at the irrational case. The irrational number, well, we'll take a very familiar number that you know is irrational, pi. Now, if you write out enough decimal places, pi starts looking like 3.1415926.535 ... out to infinity. And remember that that's non-repeating, because that is an irrational number. Okay, how would I then define, say, a to the pi power? Well, here is the way that we will think of it. And the proof of this is in calculus, as I say, but I think the idea is clear enough. First of all, a cubed is defined. I'm taking the first digit of the expression for pi. Now, a cubed is certainly defined. That's no problem. Then look at a to the 3.1. That is also defined. So I'm taking the first 2 digits involved. A to the 3.1, 3.1 can be written as a fraction, in particular 31/10, and that is certainly defined. Well, then a to the 3.14 is defined, taking the first 3 digits, and I think you see where I'm going with this. I simply continue. A to the 3.141 is defined, etc. And if we were allowed to go all the way to infinity, we would say that in the end, if I draw a big arrow here, in the end, what's happening? This approaches a to the pi, because the exponent here, or power, is getting closer and closer to the actual value of pi. Now, we'll never reach there in a finite number of steps, but for our purposes, we can believe that this exists because it looks like this is heading toward it. And that's certainly sufficient for this course. And that will apply to any situation where you have a base which is greater than 0 and some complex or some irrational number as a power, whether it's square root of 2 or pi as in this case. So you can be perfectly satisfied that a to the x will make sense. Okay, let's go ahead and remind ourselves of a few things. Theorem. These are the laws of exponents. Now, these exponent laws we saw before in this course, but when we saw them, they only applied to rational powers. Now we know that I'm going to state that they apply to irrational powers too. So that's good. The same laws you know will simply continue to be true. So let me just write this out in a compact fashion. If, say, s and t are real numbers, and a and b are greater than 0, so a and b will be the various bases here, then, as usual, I'll even write that down, as usual, we get all the standard exponential laws. So I'll put them all on one page here. On the left, I'll write a to the s times a to the t is equal to a to the s plus t. A to the s to the t power is a to the s times t. We'll multiply in that case. If you have a times b to the s power, that's a to the s times b to the s. 1 to the s, of course, will always be 1. A to the minus s means 1 over a to the s, which of course can also be written as 1 over a quantity to the s. And finally, remember that a to the 0 will be equal to 1. Now, those are all rules that you should be very familiar with by now. I'm just restating them to make you realize that the s and t now here, which are the various powers throughout, are real numbers of any kind, including, among them, rational numbers and irrational numbers. Well, with that as the setup, we can now define the function that we wanted to talk about in this segment, the exponential function. So, an exponential function in standard form, this will be the standard form we always use, of course. Standard form is f of x equals a to the x. That is the standard form. And the a, I've already used the word briefly, but the a is called the base of the exponential function. That's the word that's often used. So be sure and learn that. We're going to be using it when we talk about logarithmic functions too. Where, got to put our conditions on a here, where a is greater than 0 and a is not equal to 1. I didn't mention why we left out the 1 case, but that's just because it's easy. It's too trivial. When a is 1, this becomes 1 to the x, which is always going to be 1. And we might also mention while we're here that the domain of this function is all real numbers, because any real number, x, can act as a power, and that's what we saw previously. Well, what does that mean? Let me be a little bit more specific about the a's here. These a values greater than 0 and not equal to 1. I think it's easier to visualize this situation. Here's the situation. If this is 0 and this is 1, then we're not including 0, we're not including 1, but we are including everything between 0 and 1 and everything above 1. That is to say, there are two cases for what a can be. Case 1 is that a can be greater than 0 and less than 1, or case 2, a can be greater than 1. Now, we will see this throughout the rest of this unit, where we talk about breaking a into two cases. There will be different sorts of exponential functions and different looking graphs, etc. So that's a natural question. How does the choice of a here affect the graph of the exponential function? Well, that's a great question. I think it's time for you to do a little work, though, to explore this before I talk about it. So let me give you a problem. And you'll need your graphing device for this. Here's the problem. On your graphing device, first I want you to graph all together, that is simultaneously, 1.2 to the x, 1.5 to the x, 2 to the x, and 2.5 to the x. And you can use this window. It's a convenient window, -5 to 5 by -1 to 5. Then once you've looked at that and looked at your observations from that, then you can delete all of these and graph all together the following: 1/3 to the x, 1/2 to the x, and 4/5 to the x on the same window as above. And in both of these cases, record your observations. And then when we come back, we'll talk about what you saw, and I'll give a couple of examples. All right, you've had a chance to explore a little bit. Now let's go ahead and draw some conclusions about what you saw. The first set of examples I had you look at all had an a value that was bigger than 1. Well, let me take one of those and graph it and show you the observations that I've made for f of x equals 2 to the x, say. Okay, solution to looking at the graph of this. Well, here I will observe that the base, a, is equal to 2, and that's greater than 1. So that puts it in that one category of a greater than 1 graphs. I will remind myself that the domain of this function is the real numbers, so it is defined for all real numbers. I observe, as you did on your pictures, that 2 to the x always seems to be greater than 0. It is always above the x-axis. So that would say that the range of this function is 0 to infinity. And you might sketch it sort of schematically, if this is x and y, that the graph's action, everything that you see in the graph, happens above the x-axis. You should also have observed that there were no x-intercepts. The graph never struck the x-axis. And for a y-intercept, that was what was neat to see on the graphing calculator, I hope, is that you saw the y-intercept very clearly. The point 0f of 0 turned out to be, well, here it would be 0, 2 to the 0, because f of x is 2 to the x. And of course, 2 to the 0 is 1, so 0, 1 is the point that they all pass through. And you should have seen that in your pictures. Let's continue writing down some observations for 2 to the x. As we went far to the left, let me write that this way, as x goes far to the left, negative infinity, so draw a big arrow here like that. What happened to 2 to the x? Well, f of x, which was 2 to the x, went down to 0, you should have seen in your picture. And if you look at it the other way, as x goes to infinity, that is to say goes out to the right forever, then f of x, which is 2 to the x, seems to grow up to infinity. Okay, that's something you should have been able to see in your pictures. It is also clear from the picture that f of x equals 2 to the x is an increasing function. From left to right, it goes upward. So, by the theorem we had previously in the previous segment, so it's 1 to 1. Any function that is increasing is automatically a 1 to 1 function. Well, that's great. Now we have all this information about this, and now I'm going to give you something even more interesting. That 2 to the x is representative of the entire class of exponential functions whose base a is greater than 1. Everything we've just said about 2 to the x is going to apply to those. In fact, let me write that down as a fact. This makes graphing these very nice, especially when you're doing these by hand. All f of x equals a to the x for a greater than 1 have the same properties, thankfully, as 2 to the x, or any other representative function where the base is greater than 1. But 2 to the x is simple. So to put this all together, let me draw you a picture in which everything appears. A is greater than 1 is the case we're looking at. And here is a set of axes. And the curve that you saw on the screen should look more or less like that. It curves up from down here near 0 at the left and goes to infinity at the right. So there are my x and y axes. This is the point 1 that passes through, and every one of its class passes through. And let's mark a few other things. This here is the y equals 0 line. Of course, that is a horizontal asymptote. That's something else you should have been able to see from the picture. The various pictures you looked at. It certainly seemed that way there, and that in fact is true. This is that point 0, 1 that they all pass through. Also note that if we come over here to 1 on the x-axis, 1 on the y-axis is special. 1 on the x-axis is also special because the point up here that corresponds to it is, think about the function now. This is the function. Don't have it on the page, so let's go ahead and mark it. This is the function f of x equals a to the x. When x is 1, f of x equals a, the base. So this is a, the base, which means this is the point 1a. So those 2 points are important and will always occur on every graph of a function where the a is greater than 1. There'll always be a point 1a and the 0, 1 point. What else can we say here? You might observe, and I'll sort of slip it in over on the side, if this is the 0, the x-axis, then notice the relationship of 1, and here's a. See, a is greater than 1. A here is greater than the 1 down here, as you might expect, since that's the one we're looking at here. Let's see. A is going off to infinity, so it's going up to infinity. A to the x, I'm sorry, is going up to infinity. And it is certainly clear here that it is going down to 0 as it goes to the left. And I think that pretty much shows all the facets of this function. It is one that looks like this. Everything that has a greater than 1 will look like this. Okay, let's look at the other case, which you also explored with your calculator. This is the a greater than 0 and less than 1 case. Okay. In this case, again, I'll look at an example. I'll pick one of the ones you looked at. Well, I take that back. I don't think I marked this one. Let me check here. Yes, that was the first one you looked at. G of x is equal to 1/3 to the x. Okay. So we'll look at that, and we'll examine it the same way we examine 2 to the x. Well, here, a is equal to 1/3, which is less than 1. Again, the domain of this function g, is all the real numbers, in the same way that the other one was. All of these exponential functions will have the same domain. Observe here that 1/3 to the x, based on your picture, certainly also seems to be greater than 0 always. So again, that makes the range of the function equal to 0 to infinity, as before. There are, once again, no x-intercepts. So this is looking very much like the other one, it seems. There are no x-intercepts. As for the y-intercept, well, as you know from the picture, it's the same one as before, 0 g of 0. In this case is 0 1/3 to the 0 power, which of course, as usual, is 0, 1. So that same point, again, turns out to be a point that the exponential function in this case passes through. Well, let's collect some more of that information. What's different here seems to come out now. As x approaches minus infinity, that is to say, goes to the left, g of x, which was 1/3 to the x, instead of going down to 0 like the other one does, goes up to infinity. And in the other direction, as x goes to infinity, we saw that g of x in your graph equals 1/3 to the x went down to 0. So this is exactly the opposite of what happened for number 2, which was greater than 1. This is 1/3, which is less than 1. So we apparently have the opposite situation. And it is clear, too, that g of x is, again, opposite. It is decreasing. So it is a decreasing function. Hence, it, too, is 1 to 1. So this function where we have a base 1/3 which is less than 1 is also a function that is 1 to 1. And so I can write down the same fact I had before, except I modify it for the case 1/3. All g of x equals a to the x, where a is between 0 and 1. All of those functions have the same properties as 1/3 to the x. So if you know what 1/3 to the x looks like, you have qualitatively the graph of all of these others. Now they will vary as the base varies, of course. Some will be wider, some will be narrower, but they will all have the same basic properties we listed above. And just to complete the picture here, as I did before, for a greater than 0 and less than 1, here's the kind of general picture you should always expect. The curve this time starts up at the left and goes down to the right. So it looks like the previous one, except it's reflected across the y-axis. That's a good way to look at it. Passes through 1 here. And if we come to 1 down here, notice that the 1 goes up to a point which is below 1 here, A. And that makes sense because with my little diagram over here to remind you where A is in respect to everything else, you have A here and then 1 is above it. So A is greater than 0 and less than 1. And of course that's what you expect in this case. What else can we say here? Well, we can say as before that y equals 0 is also the horizontal asymptote for this one. So that repeats. And let's see, this is the point 0, 1. And this point here is the point 1a. So they are both on the curve as before. And the curve goes up to infinity over here. So it goes up to infinity, and it goes down to 0 on this side. Exactly the opposite of the other functions, 2 to the x and the like. So I think that covers everything for this function. All the ones, for this class of functions rather. So here's my summary page for exponential functions with base a. So they look like this: f of x equals a to the x. And the a's come out of the region 0, 1, or 1 to infinity, not including 0 or 1. The domain is always the real numbers. The range is always 0 to infinity. There are no x-intercepts. The y-intercept is 0, 1. Horizontal asymptote is y equals 0, the x-axis in both cases. F is 1 to 1 in both cases, and passes through the point 1a. Here we have a picture for a between 0 and 1. Of course, it's going downward. It's a decreasing picture. For a greater than 1, it's going upward. It's an increasing picture. So there you have, as a summary, all the information we just learned about exponential functions. And now we'll take that information and do what we have been doing all along with functions and shift them, stretch them, compress them, and the like. So let me do an example to show you what I mean. Let us graph this one. Say f of x equals 2 to the minus x minus 3. Now there's not much there to do, but it'll give us a little bit of practice. So here's my solution, and again I'm going to do this by hand. It's good to practice this. Some graphs you ought to be able to graph by hand without very much difficulty. We'll start out with what you might think of as the core function here, the function 2 to the x. Since 2 is greater than 1, this is the way that function looks. Okay. Then what next? Well, let me look at the version that is 2 to the minus x. I have that 2 to the minus x up here. Let's look at that next. Well, remember, 2 to the minus x can be thought of as 1 over 2 to the x, or if you like, as 1/2 to the x power. Aha! That's an exponential function with base less than 1. So that suggests what's going on here. It also confirms that putting a minus x in place of x is a reflection across the y-axis. So we get both observations out of this. And here is what the picture now looks like. It has been reflected across the y-axis, or you can think of it as 1/2 to the x, which is an exponential function that is decreasing like that. Finally, we have the last case, which I think I can slip in here. This is the case where we have 2 to the minus x minus 3. And that is the actual function up here. And the minus 3, of course, is a vertical shift downward. So I'll have a picture that looks a bit like this. Here's my x and y axes. And what has happened here to the line that used to be the y equals 0 asymptote, it's shifted down by 3. 1, 2, 3. So there's minus 3, and that's my location of my asymptote. And then my curve is going to come down and do something like this, passing 1 unit above minus 3. That's minus 2 here. And there it is. There's the graph of the function, and I did it fairly quickly, just using what I know about shifts and reflections. And that's what you should be able to do also. Okay. Well, I think you need to practice a few of these. You need to practice these with bases that are not only greater than 1 but less than 1. And once you've done some of that, we'll come back and we'll talk about a very special base, a base that will be most important for the rest of the course and for calculus. Now, as I said, we'll look at a special base, a base that will cause the function to be called the natural exponential function. So that's what we want to look at now, the natural exponential function. And the first thing I'm going to do is go ahead and define the base, all right, the new base, e, that we haven't seen before. So here's the base. It will be denoted by the letter e. That's traditional now. And I need to tell you what this number is. Now, I have to be honest, I can't define this in full detail without the notions from calculus. But I can give you, again, a pretty good idea of what this number is. E is that number which the following expression, 1 plus 1 over n, all taken to the n power, approaches as n grows without bound, as n goes to infinity. So if you write this expression down and you let your n's get larger and larger and larger, you will approach a particular number. Now, you have to just believe me, because the existence of e is a calculus question. Okay, we can't prove it here, we don't have the tools. Also, you'll have to trust me on a few other things. E is, in fact, an irrational number. E is an irrational number, just like pi is an irrational number. But again, you'll have to trust me on that. E, if you calculate it, and this is something you can check on your own by putting in larger and larger values of n, you can get a better and better decimal approximation to E. E is approximately 2.71828, etc. So what we often do is truncate it and write that E is approximately 2.71, truncating after the second decimal as we do in this course. Okay, so that's about what E is. And finally, let me mention that on your calculator you'll have keys that allow you to calculate E and e to the x, which is the function we'll be looking at in a minute. The keys will look like this. They'll either look like e to the x or sometimes exp of x, where the exp, of course, stands for exponent. So, those are some of the facts about the natural exponential function. Let me give you a remark here, because you may not feel very confident about this particular number e, because it's a new number. It's not like pi, something you've seen that was involved with circles. It's really kind of a special number that it doesn't seem to turn up in elementary mathematics. But e is the most important. It is the most important. And the word we use is natural base. Of all the bases that you can use for an exponential function, e is the most important one. And it's called natural. Again, I can't explain really why it's natural, because it's a calculus idea. But if you'll just accept that it's important, I can go ahead and define now the natural exponential function. And you know what it's going to be. The natural exponential function, is, well, what else? F of x equals e to the x. So the base is e, that new irrational number, and that's what the natural exponential function looks like. And just for the record, what will its graph look like? Well, e is, remember, about 2.71, so it's bigger than 1, which means its graph is going to follow the pattern of that class. So just to gather that information here, the domain of e to the x is all real numbers, and since e is greater than 1, its graph is going to resemble the following. It will be one of those that follows that class's picture, starting low at the left and going up to the right. And of course, it has all the usual attributes. 0, 1 is on the graph, and if I go to 1 on the x-axis and go up to the y here, I get the value e, so that's the point 1e, which is on the graph. And so this is the graph of this function, and that's its general shape. Now we're going to explore this in more detail as we go on. But before I did this, there's one more thing I wanted to show you. I keep saying how important e is, and I've given you a way of estimating it numerically. Let me give you 3 ways to visualize e. Now you don't have to memorize these are just for your benefit, to give you a sense that this is really an important number. 3 ways to visualize the number e, which we defined earlier there. First way, e is the slope of a particular line. It is a slope of the line tangent. Takes longer to write out than to show. Tangent to the function, that f of x equal e to the x, the natural exponential function, at the point that we noted on the curve 1e. So, if I draw a quick small graph here, there was a point here for 1 and e, and if you look there at the tangent line has slope. The slope of that is e. Okay, so there's one way to see that e occurs fairly naturally in a picture. Here are 2 others that are area related. Here's the first one. Again, this is the f of x equals e to the x curve. And here is 1. And if you take all the area under the curve, starting at 1 and going to the left all the way out to infinity, guess what that area is? That area is e. So e represents the area from 1 backwards all the way out to infinity. So that's a way of looking at e. And here's the final one. And this brings back an old familiar favorite function of ours. This is the function you recall 1 over x, which has 2 pieces like that. If you go on the 1 over x curve and you find the point 1 on the x-axis, and then you go over as far as e, then e is the number that makes the area underneath there equal to 1. So if you're going along there from 1 and you want to know when do you first have a unit's worth of area, that will happen when you reach e. So, although these will not be something that you have to worry about being tested upon, these are ways of visualizing e that show you that e turns up often enough to have some sense of being natural. Exponential function. Time to look at a particular example. Show you the kinds of places where this gets used. All right. Let R be the percent of people who respond to an advertisement, and purchase a given product after t days. Now R can be modeled by this function in the middle. R of t equals 50 minus 100 times e to the minus 0.3 t. We're not constructing the model here, we're just going to accept it. And you see that this natural exponential function appears. Questions I want you to try and answer now are, what percent has responded after 10 days? That's question A. Question B, what is the highest percent expected to respond? and see how long before r of t exceeds 40%. Remember, r is measured in percentages, in percent, and t is measured in days. So try to answer these three questions, and when we come back, I'll show you what I did on them. Now we're back on the pad, and we can see what I would have written for these. Well, here's the function that was on that previous page. I'm going to rewrite it first because I think this may be helpful at some point, and just because I have this natural inclination to get rid of negative powers, rewrite expressions without the negative powers present. So this becomes 50 minus 100 over e to the 0.3t. So the negative power is now gone. And I don't know if that'll help me, but it certainly makes me feel better when I'm trying to analyze how this fraction will change as the time in days grows. So, part A, t is equal to 10 days. And I want to know what percentage will occur at 10 days. Well, that's an easy question. All I do is use the model, put 10 in for t, and solve. So, that will be 50 minus 100. And I'll use the earlier form now, because that works best for a calculation like this, minus 0.3 times 10. But remember, 0.3 is 3/10, and 3/10 times 10 is just 3. So this is 50 minus 100 e to the minus 3. Now that's all I'm going to do here. I am then going to go to my calculator and approximate and get 45.02. So that is a calculator, truncated, of course, decimal approximation to the result, so it's about that much percentage after 10 days. Okay, well, let's go to the second question, which was, what is the highest percentage possible? Okay, well, the highest, let me go ahead and write some things out here. The highest percentage possible means, in our language, to maximize r of t, which is the function in question. So we want to maximize that. We want to find out how big it's going to get. Well, here's a case where observing something about the function is worthwhile. Remember what we had. R of t written in my second form here, 50 minus 100 over e to the 0.3t. And let's do a little analysis on this, and then we'll see if the graph will confirm what we learn. As t grows, as time goes onward, 0.3t also grows. That's just a multiple of t, so it grows. E to a power that grows will also grow. But this is on the bottom of a fraction, which means the fraction will shrink. And if t goes all the way out to infinity, the fraction will shrink away to 0. So since this fraction is subtracted away from 50, it looks like the biggest that r of t will ever get is 50. Because at any given time, it's less than 50, and only when time goes on to infinity does this drop away and we get 50. So it looks like, it seems, that as t goes to infinity, r of t goes to 50, which of course is 50%. And that would seem to be the answer to our maximization question. But I want to confirm this with a graph. So let's look at a graph here. The window that I used was 0 to 20 by 0 to 50. That seemed to be reasonable with a little bit of experimentation there. And here's the picture I got as a result. Got my axes sitting nicely here in the corner. And the curve looks something like this, where it's approaching this height of 50%. And this is t, and this, just for the record, is r of t. So I feel pretty good that that is indeed the correct answer there. I've discovered where the maximum seems to be. And finally, let's get to the third question, and I'll come back to this picture because that picture will help us with that question. On C, I want to know when will r equal 40%. So r equals 40% when? Well, the way to answer that question is to say r is 40, and that equals 50 minus 100 over e to the 0.3t, my second form. And I want to know for what value of t this will be true. In other words, at what time, which is a when question. Well, now I can simplify this. I can do a little bit of work. I can't do it all the way, as you'll see, but I can subtract 50 from both sides and get minus 40 is equal to minus 100 over e to the 0.3t. And then, if I like, I can divide through by this minus 100, so that will divide through on both sides. And if I do that, let's see, I'm sorry, I subtracted my 50 from 40 and I got 40 again. It should be 10, minus 10. And divide by minus 100, I will get 1/10 on this side and 1 over e to the 0.3t. So that means 10 is equal to e to the 0.3t. And unfortunately, I have to stop here because we have not yet examined how one would do this. How would one get the t down from being an exponent above? We haven't analyzed how one would do that, so we have to stop here. However, we can use the graph and say your trace, or if you have another key that'll take you there, to get to the point t comma 40. And what we get in that case, we will find that t is approximately then 8, which of course stands for days. Now let me bring back the picture I had a moment ago. Here's the graph we made. And what I'm saying you should do is 40 is up here somewhere. If you trace along the curve, there'll be a point where you cross there and you'll reach something of the form t40. Well, then just come down here, or read it off the picture here, what t will be. And in that case, t, as I said, is approximately 8, which is 8 days. So that settles that problem. And on that, we'll stop with the exponential function and move on to the next half of this, logarithmic functions.